Hello there, folks. Can everybody see and hear me? Please raise your hand if so. All right, looking good here. So today we're going to get into the bridge section, as I mentioned at the end of last class. We will be doing that contest. I will remind you of the rules of the contest in a little bit as we get there, but we got a lot of stuff to cover today. So I'm going to go ahead and get started. Are there any questions that I can address about the HTML that we did on Monday? I know we went pretty quick on that. I know that some of y'all are watching the YouTube videos. That's wonderful. I do appreciate it. I hope that we got all of your issues accessing the webinars addressed. If not, please feel free to email us because, you know, that's what we're here for. So if there are not any questions, I'm going to go ahead and get started on bridges and bridge designing. So when we build bridges, there's a couple things that we have to take into account. The first is the forces that are acting on the bridge, or that will act on the bridge once it's built. The first being compression. So compression is basically squeezing something. So if we took a piece of paper and squeezed it, so our hands are sort of flat with paper in between it, that would be compression. Paper stands up pretty well to compression. Now this is in contrast to tension. Tension is kind of like a pulling force. So if we were to take a piece of paper and pull it, it probably wouldn't be too difficult to break it, right? So paper itself does not stand very well into tension. Similarly, bridges will experience both tension and compression, as well as this next force here, which I'm going to call shear. If you pull a piece of paper on diagonal corners, you can see how well a piece of paper would correspond to shear forces. Yeah, unfortunately your paper bridge is not going to work too well. It might work okay for like an ant, but I digress. So I'm going to send you a link to a website really quick. You don't have to worry about this right now, and I'll put this on Edmodo at the end of class actually. But this website is a good place to, see if I can go to the website now, to check out what I'm talking about specifically. So let's take a look here. I've loaded this site. I've got the word forces here. We can see how different materials respond to these stretching and squeezing forces. So if we were to squeeze in compression, say, I don't know, a piece of paper, not a piece of paper, but like a block of wood, that's what you would be doing, and that's what bridges have to deal with. Notice there's also stretching, bending, sliding, notice that shear, and torsion. Bridges are all subjected to this, or to these forces that we have to worry about. We also have to worry about the loads that are associated with bridges. The bridge has to be able to support itself. If a bridge did not support itself, it wouldn't be a very good bridge. Now would it be? We call that a dead load, just the weight of the bridge on its own. Now a live load is weight the bridge is carrying. Now that could be a person, it could be a car, it could be an elephant for all I care. Bridge is going to be carrying something that isn't always going to be on the bridge. Bridges have to deal with static loading. So if we have a live load on the bridge, they would be sitting still. Basically, it would be like a parked car on a bridge. We also have dynamic loading, meaning that the load is going to be moving across the span of the bridge, so like a car crossing a bridge. The next type of loading we've got is thermal loading, which is load created by the atmospheric warming and cooling of the bridge. So I'm not sure if y'all know this yet, but you'll learn that generally when things get warmer, they expand and get bigger, and when things get colder, they contract and get smaller. This is no different for bridges. Now, with some bridge materials, specifically steel and cast iron, this is a serious issue, considering they conduct heat from the sun very, very well. But I'll get into materials in a moment or so here. And the last loading, or not the last loading, second to last loading, is earthquake loading. Obviously, this does not happen very often, but you do have to consider that, especially if you're in an earthquake-prone area. This loading happens during an earthquake when the earth is shaking. That's going to make the bridge a little bit, you have to worry about the integrity of the bridge after an earthquake. So you have to make sure that it's able to do enough flexing so that it does not just straight up fall over. I believe the last load is going to be the wind load. So especially with bridges in windy places or really high up in the air, wind will affect a bridge, obviously. If anyone's familiar with there was a bridge that ended up failing catastrophically when the wind hit it. It was called the Tacoma Narrows Bridge or something. We'll get to that a little bit later, but it's a really cool video of wind shaking the bridge into its resonant frequency, and the bridge is going crazy. I'll have to show you this. It's really nuts to watch. But obviously we don't want that to happen. Have I heard of the bridge made of eggshell? No, I have not. But definitely feel free to keep speaking with me about it. I'll address what you say as you send it in. They had it torn down. Gee, I can only imagine why they tore down an eggshell bridge. I feel like that's not the best idea. I don't know why they thought that was a good idea, but I guess it's a cool concept. It was old? Oh, okay. So just like I showed you with the Forces Lab, there's also a tab for loads. So you can actually see the different loadings on a bridge if you wanted to. Just pick one of these guys on the side here, see what happens when an earthquake's loaded. I'll go ahead and try it just for your sake. So, yeah, again, give this a try, but on your own time. I could sit here for a little bit and do that, but I don't want to waste class time doing something when I have to get to the bridge software. So there's all sorts of different materials you can make bridges out of. The oldest is probably made out of wood. Wood is nice because it is pretty cheap, pretty plentiful, and it handles tension and compression both pretty well. Unfortunately, wood is really fragile. When it breaks, it tends to catastrophically break, and the maintenance costs are pretty high on it because you have to make sure that it's still structurally sound. You got to make sure the weather's not rotting it. So this is good for not as often used bridges. We wouldn't find this on an interstate or anything. Another material we could use is concrete. It's nice because it's pretty cheap and handles compression pretty well. I mean, you can walk on it, no problems. It's fireproof and it is weatherproof for the most part. Cracks in concrete can definitely get water in them and freeze, and that's after many, many years of use, of course, but still, it does not handle tension well, so these cracks, the water that turns to ice in the cracks pulls it apart, doesn't handle that well, and similarly, it's impacted by the thermal load. If you walked on a sidewalk, we keep those gaps in the sidewalk so that the concrete can expand and contract. Otherwise, it would just crack and break, and we don't want that. We can also use reinforced concrete, which is just concrete with some metal rebar inside of it. It's also pretty cheap, and because of this rebar, it handles both compression and tension pretty well. It is also fireproof and weatherproof. But the thermal load becomes an issue. The metal and the concrete will expand at different rates in the heat, which does cause cracks that they do have to fix pretty rapidly. Cast iron is another bridge building material. It's nice because you can cast it so it forms in any shape that you want. It handles compression really well, and it is fireproof. But cast iron is incredibly expensive to work with. It's very, very heavy. If anyone has a cast iron pot, you'll know it's incredibly heavy. It does not handle tension very well, so that's why they use it for these arch bridges, and it often will break without warning. So you can see why that's a little bit nerve-wracking there. Definitely a big con. We don't want your whole bridge to break. As a step up from cast iron, we have steel as our next and I think last material. Just like cast iron, you can form it in steel in any shape. It handles both compression and tension well, unlike cast iron, and it's both fireproof and weatherproof as well. But it's also pretty expensive. And, you know, all bridges are made by the lowest bidder because you don't want to spend money. And so, not all bridges can be made with steel unless they do a cost analysis and say, yes, this is a good idea to make it out of steel. On the same page with the labs, you can also click on materials and see how materials react to tension and compression. So, again, on your own time, go ahead. You can check out the pros and cons and some applications for bridges, or for the materials, hence the roller coaster being good made out of wood. The next thing we have to consider about building bridges is the shape. The first shape we have is just a straight rectangular bridge. It's not very stable. Now, if you were to have a very big load in the center of this bridge, if it was heavy enough to break the material, this bridge would collapse. It's very weak in the center, and that's its big downfall. So this is going to be good for, let's say, again, privately owned bridges, so if it's on your property, you wouldn't see this on a road you would use generally. We also have an arch type bridge. Arches are nice because they work with compression, so it's very easy to hold up the roadway. And you can also strengthen it by adding what's called a buttress. It is basically just a block of stone to keep it anchored, and it'll keep it in compression and make it stronger. We also have this nice triangle bridge. It's actually called a truss bridge. I should probably change that because no one would ever call it a triangle. Trusses are nice. They work well with both compression and tension, and they're strongest at the points of the triangles or the trusses. So these are used a lot on railroad bridges, if you've ever seen one of those. This is one of those, so. And once again, we have this nice lab. You can take a look at the different, how these different shape types react to loading. So I'll bring it all the way up to 9. They all break eventually, but notice that a triangle and arch are pretty strong, but a triangle ends up the strongest of a rectangle or an arch. So, how to work the program you gave us, just wondering. That's why I'm going kind of fast right now. I'm going to get to how to work it, and it's coming. We'll have that in 5-10 minutes. So yeah, you're all good. So quick history, Rome was the first society to build some really, really good bridges. They used the arch type bridge, obviously. The Roman Empire was huge, and so they used these bridges to connect and maintain the empire. A lot of these bridges are also aqueducts, so they could, bring water in from other places to feed to hydrate their peoples. Arch bridges are good for river traffic, meaning, boats going under it. The reason this is, as opposed to a post and beam bridge, with arches, you don't need to have posts every 5-10 meters, so any sort of size boat can get through that, given they can get through the arches here. Bridge building really got used a lot more when iron was able to be worked. With iron, you assemble parts made in a foundry. You have to get it real hot, and then you can melt it any way you'd like. But once we hit that Industrial Revolution and worked with iron, bridges were pretty strong. You could do a lot more with bridges at that time. And once we've got iron, we can make suspension bridges, which suspend the roadway above the water. This is an early one in Britain. The first modern suspension bridge, or one of them, was the Brooklyn Bridge. It crossed a great expanse across the Hudson River. I'm not gonna lie, I don't have any idea which river it crosses, but the most famous suspension bridge is going to be the Golden Gate, which some of us made in our labs. I don't know what anyone out of Raleigh did, but it's incredibly famous. But they're also kind of flexible. And the bridge I was mentioning earlier, the Tacoma Narrows Bridge, this is the bridge that the wind got, and it got into its resonant frequency, and it was just galloping. That's what they called it. It was just swinging. So you can see this deformation in the picture right here. Luckily, this flexibility, though, can help the bridges in terms of there being an earthquake. You kind of have to do a trade-off to see if it's worth doing a suspension bridge, though. That's what engineering is about, having to make trades. So without further ado, I do want to get into using the Bridge Designer software that we had you download the other day. We're doing this because A, you can do a pretty cool simulation of bridges that you design, and B, because we're doing a contest. So the basic rules are you need to make a bridge that holds up to a load, and a load is when a truck drives over it, and it has to be the cheapest. In the event of a tie, the earliest submission wins, and let's see, you will get a gift certificate to Adafruit, and you can post your scores, and your scores means the cost on Edmodo. But when you do submit it, if you win, you have to submit screenshots showing the number of iterations in their design. What that means is you'll have to do multiple tests of the same bridge, because simulation is not 100% accurate. Sometimes things will fail before other things fail. And I'll get to what this means as I teach you, so just a disclaimer, this is how you know what you have to do. So does everybody have Bridge Designer installed? Please raise your hand and keep it raised if you have the Bridge Designer software installed. All right, hands down, who does not have the Bridge Designer software installed? You do not have it installed? All right. Another reminder to check on Edmodo. This is the file for Windows. That's a direct link to download the file. And for Mac, that is the link. Oops, did I get that right? Yeah, that is the link to the file. Remember, folks, to check Edmodo, you're supposed to have this downloaded on Monday. And if you didn't check Edmodo, then you should check the YouTube video. But go ahead and run the installation if you haven't already. I will begin speaking to those of you that have. already downloaded it, so go ahead and let's open it up. Oops, sorry. So when you open it up, what you'll have to do first, there will be a welcome to Bridge Designer. It won't look like this necessarily, because this is the 2013 version. But you should still have the option to create a new bridge design, which is what you want to click, and then hit OK. So when this pop-up loads, you might get a pop-up that says show tips. You can just exit out of that one, but please create a new bridge design and then hit OK. Yes, you will be using the 2015 version. I don't think it's going to be too different from the earlier versions, but still. They have changed the name from West Point Bridge Designer due to the military being like, Alright, so you have a Dell, it won't work on your computer, it's saying, what do you want to open it with? Are you talking about the file that I just sent? Or the, okay, so that's a Windows. The other link to it, the bridge, do you mean the software, right? Alright, if you go to this page here, you'll see the Bridge Designer 2015 for Windows computers. It's an exe file, so it should, when you click it, just run. It might ask you, is this safe? Can I run this? But you'll need to say yes. It is safe. Trust me. We wouldn't intentionally infect your computer with anything. Alright. So those of you that have it open, the first thing you'll see on your screen is something that looks a little bit like this. The design requirement is the specific rules for this contest. A civil engineer working for the Department of Transportation needs to design a two-way highway bridge across this river. You want to make sure that the bridge can carry its own weight, plus the weight of a truck loading, which, don't worry about that, I'll show you how to get that in just a second, and then to keep the cost as low as possible. If you want to check even more specifics, help buttons here. They'll give you tips for anything you press on the right side. And here is the elevation that you will, here's the schematic you'll be working with here. So it's 44 meters. You don't know what's low for a bridge cost? Hey, hold on to that thought and I will get there, alright? Because that's a good point. I don't know either, for that matter, other than what I've done using the software. So 44 meters long, 24 meters off the river is what we're looking for here. So let's go ahead and click on next. Yours will not open. What is it saying? Alright. Even though we are not we are participating in our design project contest thing, we do not have a code to do that. So when you get to that, just say no, we do not have a contest. And then you can hit next. Sorry, I'm trying not to go too fast for those that are still trying to work on getting their software working. I just don't want to go too far. To those of you that do have, or are on the same page as me with their software, go ahead and mess around with these on this side here. Keep the deck elevation as it is, but go ahead and see how your bridge differs when you click different things. So I'm going to give you all just a couple seconds to see what's going on with your software. see a bunch of code. There's some universal extractor running saying it is like debugging it. So you're probably seeing the terminal window, which is very well could be extracting some files, but is it just not opening at all even once that command prompt? No? What kind of computer do you have? Mac or PC? They keep saying error PC. Huh. Would you mind staying after class for a couple minutes so I can take a look at it? Oh, okay. You say PC, I mean you have a PC. Okay. If you wouldn't mind staying after for a couple minutes, I can help you find if there's any better ways to do it. There is no local contest code, so just hit no and then hit next. So, Marissa, I'm just going to have you watch and follow along for today. Just so I can make sure everybody sort of isn't just like hanging around waiting. But after class, I can help you do that. So I'm not sure what's going on. So notice here, guys and gals, there's a couple different configurations you could use. And the default's going to say standard abutments, no pier, and no cable anchorages. Now below all this, you'll see what says site cost. So site cost is the initial cost. That means just the cost of, you know, having a road, having a pier. A pier is, if you check out what the pier button is, this is what a pier is. It's just those things that go into the ground underneath the bridge. But you can actually see the price increase or decrease depending on which you choose. This price will be added to the members of the bridge, which I will show you what that is in just a moment here. What I'm going to do, just because I can, I'm just going to go ahead and do an arch abutment, no pier, and no cable anchorages. That's just how I'm going to do my template for now. You could do something different, but I'd recommend doing this one. And so notice that right off the bat, too, the cost for an arch bridge is going to be a little bit more expensive than for a standard bridge. We start, without even having built any of the members of the bridge, at $80,000. You can't select the pier option. You can't select pier when it's an arch. You can only select pier using the standard abutments button. Yeah, that's why I'm doing it. Just keep everything default so everybody can be on the same page here. So let's go ahead and click on next. And it'll ask for the material and the loading. Let's just keep them as it is already. Medium strength concrete with a standard 225 kilonewton truck, meaning that there's going to be 2 trucks and 2 lanes. Again, notice the benefit of having this medium strength concrete. You can also check the well, I guess you can't. Oh, I guess it's on both of them. You can see the pros and cons of each of them, but let's just keep it as medium strength concrete. And we'll go ahead and click on finish. So you should have something that looks a little bit like this. Does anybody have anything dramatically different? This looks different than mine. did earlier. This is weird. It doesn't look like this. Let me catch up on my PowerPoint as well. Alright, where am I? Oh, I guess I just didn't click the template. If you are prompted to select a template, just hit none for now. That's just a basic design that you could use if you wanted, but you'll still need to change even the template designs. How come I didn't get that either? If it tells you who it's designed by, just put your name, and then you can hit finish. I'm sorry, I didn't realize that this is different on different computers. How do you change the template? You go to File, Load Template, and then you can change it from here. So if you want the template, you can have it. I'll go ahead and just do continuous arch if you do choose a template. So the only thing that'll change is these sort of circles. So does everybody see at least the bridge? Everybody see that on your page? Or are you still stuck in the menu? Okay. Want to make sure we're all where it's at. You did when you opened it before? Okay. Oh, it worked when you opened it before. Huh. I just wonder why it didn't work this time around. It's weird. So anyways, these gray points are what we call nodes. If you look in the tools that should appear on the top right, or sorry, left of your screen, there are 4 options here. The first one is the circle, that's called node. The next is called member, so that's going to be what connects nodes. The next is select, so you can select individual nodes and members, and then erase in case you don't want something. But by default, this circle should be highlighted, and I want you to, there's light gray and dark gray of these. Actually, no, they don't matter. Go ahead and click to place a node. Why is it not doing that? Oops. Click to place a node. It should turn gray when you do place a node. You went to the setup wizard and installed it, but now it's having you install it again. That's some weird stuff. I don't know what's going on with yours, but like I said, just don't worry about getting it to install right now. Go ahead and pay some attention, and at the end of class, like I said, I will help you. So on these light faded gray, go ahead and I'm seeing it doesn't have the light gray nodes on the bottom of your page, and that's okay. What I had done, I actually loaded a template, which I forgot to do at first, and I'm sorry about that. If you don't have these light gray nodes, go ahead and click on File, and then Load Template. You can choose one of these. I chose the Pratt Continuous Arch. And then hit OK. So all the faded gray, let's go ahead and make these nodes here. The darker gray has already been defined as a node. Now, just as a point of reference, each node costs $1,000. So in your bridge, you might opt to put fewer nodes along it. But that's just your call. So real quick, I'm going to do a poll. How is my speed for today? I just want to see where I'm at so I can go faster or slower, just to accommodate you all. Alright, gonna go ahead and close it. Got mostly good, a too fast, and no opinion. Alright, I'm gonna continue my speed where I am. So just remember, if you do need, this will be on the YouTube channel tonight about 7:30. So now that we've done that, we got all of our nodes selected as nodes. The next thing we're going to do is create members for this bridge. So all of these light gray lines here, if you did choose a template, you need to draw members for. So to do that, you click on one member, keep your mouse held down, and drag it to your next member. When you do this, you'll see a very thick gray line, and that shows you that these two members are connected, or sorry, these two nodes are connected. We want to do that for all of these light gray lines here, so let's do it real quick. As you do it, you'll see a whole bunch of, you'll see a list of the members that you've created with a whole bunch of different properties of them. I'll explain what these mean momentarily when we do the simulation. So let's go ahead and, doesn't matter what order you do them in, just that you get them all connected. I also believe that all members have a certain cost to it. Yeah, they cost $6,000 each. So if you want to reduce costs, you might consider taking out some of these members. This is just a template that we're using, so these members are all just, doesn't really matter. So I'm going to go ahead and put your hands down. To those of you that have gotten this software working, please raise your hand once you've defined all of your members. You got it to open? Alright. So, just a quick reminder on what you do. I'm going to go quick, so be spry, get ready here. Go ahead on the first page and hit next on the pop-up, or actually, sorry, hit create new design and then OK. Click next on the design requirement. Click no for local contest code and then hit next. You want to, on the next page, only hit arch abutments and then click next. Oh, you already got there? Okay, cool. I didn't realize you were already that far. Alright, cool. Let's see where I am now, actually. So, you've already put the dots. Go ahead and add the members to connect them. And what we've got here is a legit bridge. We could give it a try to see if it corresponds with the design requirements by clicking this green button that's at the top left. So it's going to be giving you a simulation of what would happen if this bridge were to be built. So I'm going to go ahead and run the animation. So what you see here is a bridge that doesn't work. What happens is all of the members that are red are in compression. Okay? The more red, the more compressed they are. Anything that's blue is in tension. And obviously the bridge has already collapsed, so we've already failed because the design requirement says you have to be able to hold it as well as trucks. Alright? So this is not going to work. To get back to where we just were, where we designed our bridge, we click on the button to the left that says show the drawing board menu, or I think that's what it said. But now it'll look a little bit different. There will be some red lines on the members that failed. And since most of the, or all of the failures actually were because of compression, we see a whole bunch of red highlighted cells in the load test results here. A number greater than or equal to 1 indicates that your bridge is going to collapse. So we want all of these numbers to be less than 1. And notice that tension is not really an issue at all here. Very few of these members are actually in tension. So obviously this bridge is not going to work. But what can we do to fix the bridge? We have a bridge made out of carbon steel that is completely solid and has a cross section of 140 by 140 millimeters. Millimeters. Triangles? Yeah, you could add some more triangles, definitely. That would definitely make it stronger. What else could you do other than change the actual design? You got a message saying your model is structurally unstable. Alright, that's wonderful that you brought that up. If your bridge is just gonna immediately collapse and burn, like if it's not even possible to consider being built, that's what it'll tell you. It'll tell you your bridge is unstructurally stable. It'll give you a pop-up with, actually let me see if I can show you. Let's delete a couple members here and then try to run the simulation. Alright, here we go. And yes, you got that right. You do change the material. To get out of test mode, you click on the icon directly to the left of the run simulation mode. But yeah, so if your model's unstable, it will give you a couple of examples on how you can fix it. So notice that rectangles are not good. You need to have members completely defined and connected. But if that happens, then you need to redesign your bridge. So let me redraw what I just had. So you're stable, it held itself and the two trucks. To exit the animation mode, it's directly to the left of the run simulation button at the top left of your screen. So yes, we can definitely change the material of the members that failed. So let's click on the select tool. And if we hold down the control button on our keyboard, let's click on all the red dashed lines. Every single one of them. In fact, I'll do these two as well since I think I deleted them earlier. When we click on all these red dashed lines, we've selected them. So let's now go to this drop-down menu that says carbon steel, and we're going to change this to quenched and tempered steel. At this point, it's important to notice that there's this word that says iteration. That's what I was talking about earlier with the iteration. You have to submit the number of iterations that you did. Doing more and more iterations, like I said, A, not all simulations will behave the same, and B, it shows that you have worked hard to make your bridge as it is. You didn't just find a example bridge and use that on the internet. So you'll have to send proof of everything, just to warn you. So now that I've changed all of these materials to quenched and tempered steel, we can check that all the other materials are still this nice carbon steel. You can tell on the members menu on the side here. And let's run the simulation again and see what happens. Still wasn't enough, was it? So let me see where my notes are. Okay, so I've already talked about that. Failing's okay to do in simulations. This is why we do simulations, so people don't die. Already mentioned that. Next thing I want to go over is this option here. That should say 140 by 140. You did crossbars and yours holds itself but not the truck. Yeah, and that'll happen. Just because it holds itself doesn't mean that it's going to work well, but it's good to try a bunch of different types of bridges to see which works the best. So if it doesn't hold the truck, not okay. Well, the next thing I want to do, this drop-down menu here, the 140 by 140, that is the cross-section of your beams. So it's 140 millimeters by 140 millimeters. Would the beam be stronger or weaker if I were to go to 150? This is just intuitive. Think about it. A bigger cross-section, would that make it stronger or weaker? It's going to make it stronger if there's a bigger cross-section. Alright, and it's kind of weird, the reasoning for it. If you were to change all of these to 150, they may or may not work. In fact, let's give it a try just because I can. Change this to 150. I'm going to run a simulation. It's holding itself now, that's a good thing. But it doesn't hold the bridge still. But notice that having a bigger cross-section does make it more strong, but it makes it more expensive as well. So this is because, how do I run the simulation? You click on this sort of turquoise icon on the top left. And to get out of the simulation, click the button to the left of it. So this is because of the object's moment of inertia. And hang on, I see a question. Your bridge has to be stable to do that, correct? Yes. If your bridge is not stable and you try to run your simulation, it'll give you that unstable error. So there's differences between moment of inertia and inertia. You're probably familiar with inertia. An object in motion is going to stay in motion based on its material and weight and etc. Moment of inertia is a little bit different. It's a quantity that expresses an object's tendency to resist change. So a low moment of inertia of an object means that it will start rotating more quickly once it is agitated. So you want this to be pretty high. You want a higher moment of inertia to be good. And so I'm going to skip all this because time, and this is probably a little bit beyond where you are. This is what I did in college, so I told you how to change the material, but the best material is probably going to be steel, or, well, hang on. I haven't really gone over much of this, so I'm just going to go ahead and just trust me that steel is an alloy, meaning that it's a combination of two elements. The way that you, what was I saying there? I'm just going to have you trial and error in terms of materials to see which one's stronger, but keep in mind the quote-unquote stronger materials are going to be cheaper, or more expensive. So the way that these materials are different, even though that they are all steel, is due to the heating and cooling process that it's exposed to. Basically, if you heat something up and cool it down really quick, it becomes very, very strong but very, very brittle. And that's why this material that we chose, the quenched and tempered steel, for our weaker members, that's why it worked. That's why it was a little bit better than our initial carbon steel based object here. I'm not going to talk about yield stress. That's a little bit intense there, but another thing that could help you with this design is changing certain parts from solid to hollow. Now, hollow is going to make it weaker, but can anybody take a guess on why we choose to do a hollow members versus solid members? Why would hollow be good? It is lighter. That is going to be good on shipping costs and stuff. There's another reason, though, which I sort of given you away already. Cheap. Cheap, cheap. You got it. Just like Scrooge McDuck here. Engineering is all about being cheap. Cheap but safe. Don't worry, it's not like we're going to skimp on something just to be cheap. There is a trade-off between strength and money, though. Obviously, hollow is going to be cheaper, but less strong. So, even though most of the examples that I've done here have had mostly compression issues, keep in mind that tension, which is going to be the blue striped members, keep in mind that's also going to be an issue. And you'll actually have to do some experimentation to see what material works best where. So that includes material, if it's solid or hollow, and its cross-section. But remember, this is all going to change the cost of your project, which is sort of our big thing. Alright. So let's see if I've left anything out. Change the material, it got stronger. Again, the iterations thing, I would go ahead and just keep going on this design and changing it from there. So a couple more things I did not mention. If you really wanted to, you can add a node wherever you want. So let's throw one right here. We can connect it if we want to. We can connect two nodes that are not connected initially. And we can also take out some members. Do you save your bridge so you can leave and come back to work on it later? I would definitely recommend doing that. That's definitely a good habit to get into, saving just in case something bad happens. So for example, I just added a whole bunch of stuff here. How do you save it? File and then save as. And name it your last name. And save as. Now let's see if this one worked. I doubt it did, but yeah, not good. That's not what we want, is it? So I would know to go back to the drawing board. I just did this iteration. We can then change it to make it a little bit stronger. So for the last couple minutes of class, I want you to experiment with a couple different designs here. Just see how it changes when you change the material on certain members, its hollowness, and its cross-section. A thing to remember is that you do not want to over-design your bridge. Have you tried adding metal to hold it up? You mean a, what's it called, an abutment or a pylon or something in the middle? I haven't, but you can. You can definitely use sort of a straight bridge template. Like, let me go ahead and load one if I can. Guess I've already chosen that, but let's go ahead and do a new design real quick and I'll show you. Metal, oh, you're talking about like a suspension bridge. I haven't. I think it might work a little bit differently. I actually don't even know if you can do that, considering it's the design's just a little bit different. You can try though, and if it works, I don't see why not. Oh, you did, and it did work. Remember that you do want to keep doing more and more iterations, just to make sure that you've gotten the cheapest as possible. Remember, just because it's holding it up doesn't mean that that's the best design. If you have, say, a really, really low tension, force, strength result here, you don't need to have such a strong material in that member. You can choose something weaker for that specific member. Don't over-design. Over-designing is where money is spent, and we do not want to spend money. Another thing I didn't mention earlier, how did I change the design? I literally just opened a new design and went from there. Last thing I didn't mention, you can actually check a list of all the details of each member. So you can see what it's, I didn't talk about this, but yield stress, modulus elasticity. You can check it out compared to each other, see how much it costs per meter, and it actually gives you a nice little graph here of the strength versus the length. So for this material, a shorter length will keep it strong. If it's a really, really long length, if it's 12 meters long, it's not going to be very strong. So I do know I went very quickly. How do I make the triangle thing above the bridge? That was just me choosing a new template. Which is why what I would do is choose no template. So that way you can adjust your nodes as you see fit. Okay. So it is 5. So class is over. If you don't have any questions, you are free to go. Yeah, you're welcome. Remember to submit your cost on Edmodo by, I'm going to say Sunday evening, but we might extend it to Monday. So go ahead, work on this over the next couple days, get it to us by Sunday evening, and we will see who's going to take home the fabled gift card. So you can go if you don't have questions. If you do, I'll be on for just a couple minutes more. Yeah, no problem. Thank you for coming and asking questions and generally being here and pleasant. And by generally, I mean you are, so don't worry. All right. If there's nothing else, then I'm going to head out. Thanks a bunch for coming today, and best of luck with your bridge designs. Take care, y'all.